Okay, hello and welcome. Here we are, another video. Let's take a moment to check the audio's working, video's working. I think my internet connection could be kind of spotty. Video's working. I think my internet connection could be kind of spotty. Video's working. I think my internet connection could be kind of spotty. Video's working. I think my internet connection. Sorry about that. Alright, I think we're good to go. Yeah, I can also have a tendency to hesitate a little bit before I start. Alright, let's just go right into the next question. And sometimes I like to kind of chat a little bit about what's going on in my personal life, but I'm not gonna do that now. Just go right into it. Don't have to do that for a while. Minimum score triangulation. Minimum score triangulation of a polygon. You have a convex n-sided polygon where each vertex has an integer value. You are given an integer array of values, or values of I is the value of the ith vertex, i.e. clockwise order. You will triangulate the polygon into n-2 triangles. For each triangle, the value at that triangle is the product of the values of its vertices, and the total score of the triangulation is the sum of these values over all n-2 triangles in the triangulation. Return the smallest possible total score that you can achieve with some triangulation of the polygon. Okay, values 1, 2, 3, 6, 6. The polygon is already triangulated, and the score of the only triangle is 6. Okay, values 3, 7, 4, 5. There are two triangulations with possible. Okay, I see. So convex polygon, n-sided polygon. Excuse me. Yeah, convex n-sided polygon. Integer values triangulate into n-2 triangles. The value of that triangle is the product of the values of its vertices, and the total score of the triangulation is the sum of these values over all n-2 triangles in the triangulation. Smallest possible score you can achieve. Excuse me. This is interesting. I want to say this is probably like a graph question. Probably can do this to the graphic, convert this to a graph and use some graphing algorithm. Two triangulations, possible scores 375, 574, or 345 and 374. Okay, and the minimum is 144. The sum of the products. This is an interesting question. I'm not really, kind of threw me off a little bit. I might have to think about it for a while. Sometimes I don't get the answers. Like sometimes I get them very quickly, and sometimes I just don't know. I kind of maybe want a piece of paper to write on. I've been pondering some other questions too that I've been looking at. Some of the harder questions, and looking for ways to solve those, which sometimes they take a really long time. The hard questions. That's kind of why I usually don't do them on stream. I'll like read them, the question, and then just think about it for a while, and maybe try to program it later. Because at some point we're going to be doing the hard questions, not just the medium questions. So I might switch to hard questions once I get to like, I don't know, once I get through like another 500 medium questions. I might start going for the hard ones. Okay, here's another one. So we have 1, 2, 3, 4 triangles. Okay, it has to be n minus. So if there's six sides, got to make n minus 2 triangles, which is if you draw one line across somewhere, yeah, you either end up with 1, 2, 3. You either remove 1, so you could split into, from any particular vertex, drawing a line across, you could split into one triangle and a 5-sided or n minus 1-sided polygon, or 3-sided and n minus 1-sided, or a 4-sided and n minus 2-sided, or for given I, it's going to be 2 plus I sided and n minus I sided polygon. And the reason why I'm trying to do it this way is maybe I'm trying to think, maybe there's a top-down recursive memoization that we can do, and I want to try to figure out if there's like some kind of pattern involved. Yes. So, okay. That seems to be correct. You end up with a polygon with 2 plus I for a given point, and then if you index the points sort of I don't know, I guess clockwise, counterclockwise, whatever direction, and you say, okay, we're gonna write to that point, that index. And that would represent a certain that I value is like whatever index you need, not really the index, but how many how many points when you draw that line, how many points I guess are in that, and one of the smaller of the two, not necessarily the smaller of the two, but just how many points are in that polygon on to the right of let's do it to the right of your line, and then there's a polygon to the left of the line, right? And to the right is starts off at 3 with I is 1, and then so I is an element of 1, and then in the case of when n is 6, then we can go to 2 when I is 2, and we get that's 4-sided, and the other one is now also 4-sided, and then we can go to 3 when I is 3, and then now you have 5-sided and 1-sided, or 3-sided, excuse me, or 3 vertex, 5 I shouldn't say sided, I should say vertices. Although I think it's the number of sides of vertices are the same for convex polygons, so actually that's fine. So it's 3-sided and 5-sided. And you can't go past 3 at this point. So it's going to be from 1 to n minus I. So it's going to be 2 plus I is greater than or equal to 3, and n minus I is less than or equal to n minus 3. I don't know. I think it's n minus 1, which gives us I is greater than or equal to 1, and negative I is less than or equal to negative 1, gives us I is greater than or equal to 1 again, which is not the right side I want. I want the other side, which is actually you could do it this way. Easier way of doing it. 2 plus I, that's going to be greater than or equal to 3, and it's also going to be less than or equal to n minus 1, which means I, if we just subtract 2 on both sides, I is going to be between 1 and n minus 3. Yes, inclusive. Okay. Okay, that's what it's missing. So yeah, those are the different values for I. And basically, you could triangulate each of those. It says it's gonna be n minus 2 triangles, right? Interesting. That's going to be 3 lines total, because each line gives you, 2 more pieces, and you need n minus 2 pieces total. And so it will say P is n minus 2 total, and L, add one. If L is related to an increase in L of 1, gives you an increase of P, really of 1 actually. That means that L is equal to P. So we have L is n minus 2 lines. Interesting. Is that any triangulation gives you that many lines of a convex polygon? I think so. I think triangulation is always going to be n minus 2 triangles. And n minus 2. Well, in this case we have n minus 2 lines, n minus 2 triangles. The number of lines is only 3 lines. I got that wrong, or it's almost like I got something confused there. No. P starts off at 1, L starts off at 0. And when you increment L, you also increment P by 1. So that means that P is equal to L plus 1, or L is equal to P minus 1, which that means that L is going to be n minus 2 minus 1, which is n minus 3. Okay. Yeah. That's a little confusing. But yes, that's n minus 3 lines. So yeah. So 3 lines. You expect 3 lines. Okay. That's fine. I think basically, yeah, you just triangulate the other polygon. So yeah, I mean, a brute force approach then could just be, draw for each value of I, you get the 2 subcases, and then you just find the minimums of those 2 subcases and add them together. So you'd have like for each I in the outer loop. And the subcases, we could use an array as the input, right? An array of input. So it would be like if I drew a line from, well, they're all ones here, but if I did like 1, 2, 3, 4, 5, right? One, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6, and that array is like so. Now, if I drew a line from 2 to 5, what do these 2 arrays look like? Well, 1, 2, and now this jumps straight to 5, 6, back to 1, and the other array is, let's do clockwise, 2, 3, 4, 5, back to 2. Okay, interesting. So those are the 2 subcases. And that's a little bit strange. So yeah, 1, 2 jumps to 5, 6, and 2, 3, 4, 5. Oh wow, okay, that's interesting. Huh. Yeah, because there are, for a given index, and actually there's a few different. Oh yeah, I want to check how big is that. Oh, 50. Okay, that's not too bad. Those are between 1 and 100. So yeah, you could do 50 squared is about 2,500. It's more like 50 choose 2, which is not quite 50 squared. It's like 50 by 49 over 2, which is like 25 by 49, which is let's see, 25 by 50 is like 50 squared over 2, which is 2,500 over 2. So that's 1,250, and then subtract 25, you get 1,225. Okay. So 1,225 if you do a double loop, quadratic time, and then each of these sub arrays, when they get processed, it's actually not too bad. It's basically, I suppose I would actually just recreate the arrays in each subcase. I think that's fine, but that's going to be, it splits the array evenly into 2, not evenly, but splits the 2 cases into 2 smaller arrays with just 2 extra elements. Meaning I think you do a linear number of operations here anyway, right? And I think you end up with quartic time, 50 raised to the 4th, which is kind of a lot. Well, it's not exactly 50 to the 4th. It's more like it's quartic, but it's also, I think there's the like division by 4 in there kind of a thing going on. It's more like 1225 squared is like the actual number of operations, which is pretty manageable. Actually, it's like 1 million or so operations total, a little bit over 1 million. But yeah, I think I would recreate these smaller arrays on the split. and then recurse on those. And you can't really create a, you don't really even need to do dynamic programming here. So I'm trying to figure out if they should use dynamic programming or not. No. The answer is no. The answer is no. Yeah. You recreate this array. It's kind of just a brute force solution, quite frankly. Yeah. Recursion. I don't know what else to say. It should be fast enough to pass the test cases. Maybe not the most efficient way to do this, but it should work. Yeah. Okay. 15 minutes or so. Took me a while. I mean, I didn't program it yet, didn't finish it, but we could try something like this. I'm going to rename this to VS. VS, say const int n, it's vs.size. All right, let's try it. So int I is 1, I is less than or equal to I plus 3 is less than or equal to n. Increment I. J is going to be, so actually it's the other way around. It should be I is from, it's 0 less than n, and j is going to be from 1 to, right? And we're going to say const int target, or t, is going to be I plus j modulo n. So that's going to be the point that gets selected. It really should be 1 or 2. So move over 2, 2, 3, 4. Yeah, 2, 3, 4. It really is. Two, 3, 4. Actually, I kind of did that the wrong way, but 2, 3, 4. And modulo n. Actually, these should be reindexed to 0, 1, 2, 3, 4, 5. So 4 plus 2 mod 6. Yeah. It's from here to there. And you know, I don't actually want to, there's sort of a round robin thing going on here that I need to be careful about. There's 0 to 3, 0 to 4, 0 to 5, 2 to 4, or excuse me, 1, no, did that wrong. I realize I'm drawing here, it's not really clear what I'm doing on the screen. So 0 to 2, 0 to 3, 0 to 4, then 1, 2, 3, 1 to 4, 1 to 5, then 2 to 4, 2 to 5, but we already did 2 to 0. Yeah, I don't want to don't want the ones I've already done. That's the thing. You could do it this way too. Or I could do it this way. You could say j is from I plus 2, right? 2, 3, 4, up to j is I plus 2, up to n minus 2. I think less than or equal to n minus 2. So in this case, 0, 2, 3, and 4. Then we look at 1, we go to 3, 4, 5. No, that's not correct. You know what? It's bounded by I'm not too sure actually. Zero to 2 we already did. 2 to or excuse me, yeah, 2 to 4, 2 to 5, 2 to 0 is already done. There are a couple things here, so it's got to be less than n for sure. That'll prevent it from going over things that have already been done. And then also, in the case of 0, it's got to be less than n minus 1, which is a little bit odd. Does it go n minus 1? So there's n minus 1 plus n mod n, something like this. It's confusing. It would be I minus 1. Whatever I is, subtract 1, and we have to be less than that value. Which is this thing. Which is a little bit odd. Bound. Yeah. That's a strange one. All the other cases are fine with that, but it's just 0 one time has an issue there. I'm wondering if there's like a way to optimize that slightly. It's probably a better way to do that, but that works too, I guess. Yeah, it's got to be less than 5. So 0, 2, 3, 4 is less than 5, and then 1, 3, 4, 5 is not an issue. Oh, that's so confusing. Never mind, it doesn't work. What's going on there? Oh man. We just have one if statement in here. If it's I is 0, you just have to skip once. I is 0 and j is greater than n minus 1. Just continue. This should get branch predicted. This will just always skip the if statement. I think that's the only time. It's just one time at the end there. 0 to 2, 3, and 4. The first time it doesn't go 0 to 5. And then 1 is going to go 3, 4, and 5. It doesn't go to 0. 2 goes to 4, 5, and we already did 0. Let's go to 0. 3 goes to 5 and doesn't go to 0. We already did 0. And 3 and 1 we already did. And then 4 is going to go... it would go to 0, but we already did that. It would go to 1, we already did that. And go to 2, we already did that. So 4 doesn't get touched. And then 5 is also done. 5 would go to 1 and to 2 and to 3, but again, those were already done. So yeah, it's a little bit wonky, a little weird, but it works. Yeah, so that's I and J. That works. Now the question is, okay, now that we have those indices into the array, I want to create these smaller recursive cases. So I want const auto recurse. Const standard vector reference. Say left, or just, yeah, we'll just say vs also. Again, reverts or vals something. Yeah, I mean, all right, it's fine. It's name the same thing, or array is fine too. Okay. So this happens here. Come back to this. And we're gonna, I think it's just return this. And what's gonna happen is there's a result. So it's gonna be the int result. Turn that result. I'm gonna say, I'm gonna create these two subarrays. So if the target is 0 to 2, for example, then there's going to be a triangulation from 0 to 2, right? Plus I plus j, and right, say left and right. Let's see, they all fit into an integer. This is kind of a, it's taking me a while. It's kind of a weird approach, weird program. And then also, there's now 0 to 2 is one triangle, but there's also a triangle that goes 0 to 2. So we have 0, 1, 2. We also have 0, 2, and then 3, 4, and 5. So we would take everything from left to right, including 0. Vector, say v. And the size is going to be the size of v is going to be not n. Also, this shouldn't be n. This should be array.size. It's going to be n minus left.size, right, plus 2. Because those two endpoints will be included. Excuse me. And we could just make those zeros, I think, initially. And then we can say we're going to write in copy into v, v.begin. We're going to write in I to j, No, this is going to go from array.begin to array.begin plus I plus 1. It's going to include I. I think this is also plus j plus 1, by the way. Thinking about this here. How does it work? Yeah, that's correct. Yeah, that's fine. This includes I. Copies that into vbegin. Then we're going to copy the other part of the array, which starts off at plus j to the end of the array. Kind of involved. And this is not vbegin, it's going to be begin plus I, more or less. Yeah, the number of elements here, it's going to be, we write up to and including I. And we want to do I plus 1 then. Here. Something like this. 0 to I inclusive. And this is going to start at I plus 1 then. Position I plus 1, yeah. More or less the idea. Interesting. So we have the left side and the right side. This is going to be V. Okay. And the way this is going to work, so we recurse on the left side and right side in each of these cases, and we want to say take the left side and the right side, so the left side plus the right side, and the result is going to be the maximum of these two possibilities. And we're going to say if array.size is less than 3, return 0. This shouldn't happen. Shouldn't execute, just in case. Return the product of see something here. I think I want like a fold expression, right? I think I could do it this way. Accumulate. This is different from the left fold, yeah. Reduce is a little bit different. Reduce is out of order. Yeah, it's reduction. But you can use a different operator. You don't need to use a sum. You can do the product. So even have an example of a product that multiplies. Cool. Cool. How are we doing on time? 30 minutes? All right. It's a considerable amount of time. So this should be accumulate with array.begin, array.end, 1, and standard multiplies. I don't know if I need, I do need this. Create the object, the compare comp. That's basically it. Yeah. Create the left side, create the right side, recurse on the two, and get the maximum. Oh no, they want the minimum, not the maximum. Excuse me, not the yeah. So this should actually start off at some number that's way larger. What's the biggest number you can get? I guess if you're going to select 3 numbers, and they're between 100. All three numbers could be 100. That's a million, I think. 100 cubed is 10,000 times 100 is a million. Also, I got something wrong the other day. I said it was 25,000 when it was actually 250,000. 500 squared is 250,000, not. Made a mistake the other day. 100 cubed is a million, and then how many triangles do you have? We have n minus 2 triangles, right? So 50, it's roughly 50 times a million, so it's about 50 million. So we could do 50 million for our sentinel value, or 100 million is probably easier. Which is 8, I think. Yeah. Yeah, let's try that. Pile error. This should be actually structure union. What's going on? What? What is the problem? Huh? Runtime error. Okay. N minus left dot size. I don't think this should be an issue. Int. Oh. Of course. Duh. Oh my goodness, I didn't even think about that. Whoops. The left array is this size. Okay, I kind of goofed that up. I didn't really think about that. This is going to be the left array size, which is j minus I plus 1, I think. It's j and I inclusive, between j and I inclusive. I to j inclusive is what it's supposed to be. This is supposed to be plus 1 then, I think, by the way. It's pretty tricky the way I programmed this. Oh, okay, looks like I got it. Yeah, straightforward thing. Let's try, 50 different numbers. I like having Python scripts print my test cases. I stopped doing that because it just takes a while. Okay. All right, got it. Look at that. Hopefully it doesn't TLE. That's the thing I'm most concerned about. Can take a deep breath. No! Oh no! Say it ain't so. Say it ain't so. Oh, that's terrible. Oh, that's bad. No, really. Oh. Uh-oh. Oh. Oh. Say it ain't so. Say it ain't so. Ouch. Oh no. So brute force is maybe not gonna cut it. Brute force is not gonna cut it. Well, gee. Shoot. Well, what to do about that, huh? I gotta prune some of the options here, gotta optimize a little bit. I think it's at least a correct answer. Might not be a fast answer, but it's at least correct. Fairly certain it's correct. Oh man. Oh. Excuse me. Oh, it's still TLE's even on that? Oh no. Oh, it's gonna be a lot faster, huh? Could just be in some kind of infinite loop too. Excuse me. Oh, okay, I think it's okay. Probably is fast enough. It's just in an infinite loop. Alright, that's fine. Let me actually go back then. Keep that where it was. Let's go down to like 10, or let's go to like 20. Or maybe I'm wrong. Maybe it's not actually as fast as I think it is. Maybe it's a little bit slower. Actually, maybe I'm not calculating how fast it is correctly. So it's not cubic quarter time. I think it's quarter time. I'll copy it. I don't know. Is it an infinite loop? What is going on? Oh man. It's really taking a long time, huh? Oof. Okay, it's correct, but very slow. So I want to print out each case. So yeah, I did something wrong here. Try this out. It was definitely a lot slower than I thought it was going to be. Yeah, 10 to the 4th is only like 10,000. It should be pretty quick. But oh, TLE, whoa, oh yeah, okay, fair enough. Kind of makes sense. Let's get rid of the test cases. These are just like the base test cases. Kind of in the way at the moment. Okay. Oh, man. Yeah, TLE's now because I'm printing here. Okay. I could put the arrays in a map. Wondering if that would make things faster. That's the thing, is I don't think it should make things faster. It should be. I guess maybe that's the issue. Yeah, it's certain triangles are being like retriangulated multiple times. I could do something like the following. This could memorize. Although it should be pretty slow if I do it this way. I don't know if this actually helps. This memoization. Could try it, see what happens. Okay, that's a lot faster. 20 milliseconds. Okay. That's kind of what I was expecting before. See if it's fast enough for this. So I don't know. Yeah, I guess the memoization was what I need to do. Oh no! Say it ain't so. Say it ain't so. Gee. It sucks. Oh my goodness, really? Still pretty slow, huh? Huh. What? Did memoization do anything? I don't know if it really matters. Boy. Oh boy. Whatever I'm doing, I don't think I'm doing it right. I don't think I'm doing it right. It's kind of confusing. Oh yeah, the memoization makes a big difference. Okay. Sure. Let's go further. I don't know what to say here. What to say? Oh wow. It seems to be exponentially more expensive. I wouldn't say this is quartic time. I don't know what it is, but it takes a while. It's correct, at least. That's kind of cool. But maybe the way to go is there's gotta be a better way to do this. This is just not efficient enough. I thought maybe I'd be able to get there, but it's a little bit more complicated than I was expecting. Alright, well, I got something. Challenging question, 50 minutes. Not ideal. Well, I mean, I've got to have some triangle somewhere, right? That reduces the problem by one value of n. The question is like which triangle you're going to use, because no matter what triangulation I come up with, every pair of points I see on that outer edge has to be part of some triangle. There are really only two options per edge, right? So from 0 to 1, you can go, if we're looking at the picture, 0, 0, 1, 2, 3, 4, 5, right? The only triangulation you can have with that contains edge 0, 1 is you can triangulate 0, 1, 5, right? And now 0, 5, 0, 1, and 1, 5. Or you can triangulate 0, 1, 1, 2, and 0, 2. And every edge has only one of two possibilities, right? And then each of those gives you a subcase of a smaller convex polygon with one less smaller convex polygon with one less edge. vertex. Yeah, so you end up with 0, 2, 3, 4, 5, 0, 2, 3, 4, 5 to process, or you end up with 1, 2, 3, 4, 5. Yeah. That's interesting. And then add that those recursive cases. Whatever 0 times 1 times 5 is. V0, V1, etc. And then same thing. 0, 1, 0, 1, and 2. I could approach it that way. That's a little bit simpler, I think, than what I did here. And I might be able to use dynamic programming there as well, some form or fashion. I think that's faster. I think I could use the same approach that I used here, and that'll work. That'll still be fast enough. It's just, yeah, you would memoize the entire array each time. And I think that's still exponential time, because the number of different possible arrays is the arrays are technically different after each iteration. There are duplicate values though, so maybe it's not totally loss. Oh. That's a good question. Maybe you could memoize in the following way. It's going to be because these two recursive cases, it's going to be f of 0, 2, 3, 4, 5. And the other one is f of 1, 2, 3, 4, 5. But the 2, 3, 4, 5 part is the same in both cases, and I could just put that as an index j, and then the other is just some value v val. So it could be f of val j is the function that gets called. And I think as I go left to right in that way, in that sequence, then j just increments at every step. And that's relatively straightforward. And then val just gets changed. The number of different values is only between 1 and 100. So yeah, it's a little bit complicated, but ends up being that function gets memoized over 100 by 50, which is only 5,000. And I think it's pretty efficient if it works that way. Let's try that. Might be able to do it, not using a top-down memoization, but just have a pair of values. Even actually further than that, you could just do integer arrays. Say m is Falstad size, or actually let's do n. Excuse me. Could go even further. Let's do n. Bound is 101. I'm going to say for each I 0, I is less than n, increment I, fill memo of I plus bound zeros initially. And then we'll say, probably should even go further and go with an optional. I like that. And now index, and we're gonna say if not memo of val index, if memo of val index exists, return that. Let's just say for optional. If optional exists, return it. Okay, it's a little bit better. So the index, it's greater than, so the index should be, so it's gonna be there's n minus 1 and n minus 2 and minus 3. The index is gonna be starting on that leftmost value. So n minus 3 is when we're gonna say accumulate vals. Plus the index. And if this is greater than or equal to n minus 3, this shouldn't execute, but we can just return the maximum value. Okay. All right, try these things. And now we can say, it's simpler. It's gonna be, it's gonna be the first two values. So the input is 0, 1, 2, 3, 4, 5. And we're gonna take 0, 1, which val is the beginning part. Give me a moment here. Hold on a second. Back. I'm actually gonna go ahead and just make this not visible. Okay, I'm back. Oh, it's not that late. It's only 6:40. It feels like it's like midnight. I'm gonna have to cut this video before I submit it or upload it. Yeah, I went to chat with some folks and I totally forgot that my live stream is going. Sorry about that. Very awkward. Yeah, but we're back here. Okay. Yes, challenging question for sure. But yeah, I was saying I could use optionals and accumulate. So it's gonna be top-down memoization. Kind of don't want to go through all of the. I'm probably sure there's a DP solution you could use too, but I'm not gonna go through that here. Yeah. So what happens is you have the left side and the right side, which is three things left is here. It's just return. Result is going to be that sentinel value. And we're not going to memoize just yet. It's going to be the left side and the right side. So it's the first two values, which is going to be index array of index. Come back to that in a moment. So f of a little confusing here. Okay, we have left, we have right, we have the index is incremented by 1. Always. Right, index is always incremented by 1, and we also say the value here. Interesting. I don't think I did this correctly. Oh no, it's fine. So it could be 0 or 1. This is going to be the. Okay, so we'll say val is going to be array of index. Or not val. Or v2 even, I could say, or next val. Okay, so we have 0 and 1. This value, one of these is val and one of these is next val, which is very confusing. As to which is which. It's going to be val times next val times something else. Val times next val times something else. Okay, this one, if you have val and next val and then f of val starting here, you're going to get the back. Array back, basically. On the other side, it's going to be array of I x plus 1. Yeah, that's a little confusing. 0 times 1 times 5, the other side is 0 times 1 times 2. Interesting. And we want the min of left and right. We don't need the sentinel value. And it's going to be memo val and ix. Yeah. Okay. Interesting. This isn't quite right because this val is supposed to be basically the beginning of the array. Excuse me. The beginning of the array. And so really it should be a size 2, not 3, ix plus 2. Okay. Multiply val by that. This should never really happen, quite frankly. Now this also could be turned into a DP solution. This particular approach, if this works, I think this could be turned into a non top-down memoized DP solution. Give me 1 second here. Thinking if there's anything else I need to do here. Is this it? I could try it to see what happens here. This might be probably wrong, but probably some mistake somewhere. Sure. Oh, this is vals now, not array. Should probably rewrite this to array, actually. I'm using val. Val and val is a little bit too close, I think. Words. Oh, this should be array as well. Okay. This is now 0, 1, I think. Something like that. Not 0. Array of 0. Whoa. Oh, no, don't do that. Don't want to show things here. Did that wrong. Still wrong. Okay. It's fast though, but correct. All right. Interesting. This just goes up to 16. Okay, let's do the test case, original test cases. I'm only getting 0. All of them are 0. Okay, so we would recurse value index. Array of 0 is 1, and index is 1. So it would be 1 and 2, 3, and then we would say, oh, that's probably why. That might be why. kind of forgot about that. Oh, okay. Interesting. Oh, okay. Got those two mixed up as well. Forgot that I kind of optimized that a little bit, put the bound on the right side. Okay, wrong answer. Correct here, which is cool, but wrong here. All right. So what happened here? So 3, 7, 4, 5. 3, 7, 4, 5. And then that breaks into two pieces. We have 3 times 7 times 5 plus 4, 5. Yeah, it should be 3 to 7, that edge, and it goes to let's say 3, 7, 4, 5. We either go to 4, one edge goes to 4, one edge goes to 5. So the edge that goes to 4, we'd have 3, 7 times 4. 3 times 7 times 4. And what we'd have left after that would be 3 f of 3, 4, and 5. Okay, that's one. The other one is 3, 7, 5, and shift over to 7, and have 4 and 5. Okay. So one of them takes the front, the other one takes the back, but the next value, that's kind of the important part. In the second case, we take the next element to the right. There we go, 3, 7, 4, 3, 7, 5 rather. Or excuse me, take the value from behind, 3, 7, 5. Then this ends up being we move the value to 7, right? Which is here. Yeah, okay, that's fine. It's left side, right side. It's actually the other way around. This is right and left, but it's fine. We're going clockwise. We'll just say 1 and 2, depending on the how you think about this. But yeah, going to the right would be the first one, 3, 7, 4, which is value. Next value is 7, and then last value is actually not the back. That's not correct. This one is array of ix plus 1. And then f is going to be the same current value plus ix plus 1. Yeah. And then that's on the right. When we go to the right, we go 3, 7, 4 to the right. Go to the left, the point to the left, we have 3, 7, 5, which is the back here. 3, 7, 5. And then now we jump forward to next value. So that was a little bit mixed up. It's fine. Just draw a picture and try to address it again. Okay. So that works correctly in that case, but this one is wrong. So now we have 6 points, right? 1, 2, 3, 4, 5, 6. 1, 3, 1, 4, 1, 5. Okay. So here we have 1, 3. We can go to 5, or we can go 1, 3 to 1. And the correct answer for the solution should be going 1. Oh, okay. It's kind of rotated. They have is that 1, 1, 4, 1, 5, 1, 3. They start in the bottom left corner. So we just rotate this twice. All the ones I think are connected the way they did this. Yeah. Okay. So yeah, this could be 1, 3, 1, which is 1 times 3 times 1. It's going to be f of the same value, and now the same value, and then 1, 4, 1, 5. So we had 1, 3, 1, 4, 1, 5, and we started with 3, 1, 4, 1, 5, and now shifted off that 3 value. Right? This first. This might be wrong, this idea. It's kind of a, I don't know, trying to figure it out, I guess. Try to see if it works. So it would keep that same value. The I plus 1 x value is an array of index I, and then I plus 1 there. Okay, and then we start at that I plus 1 position. Keep going to the end there. Okay, that's fine. And then the next iteration here is now we're looking at f of 1, 1, 4, 1, 5, which this is oh, that's interesting. So you don't necessarily need to add a triangle here. Oh, I see. Okay, never mind. So my idea was wrong. It's a little more complicated than this. Oh, I see. Okay. Well, it's true that every edge has to be part of some triangle. It's not necessarily the case that every edge is going to be part of a triangle that connects directly to the side, left or right side. Although I think it's true that at every iteration there's going to be at least one such edge. So that's where things get confusing. So you would say for each index, let's just say I or j, starts out at index, something like the following. Yeah, it gets okay. A little more involved. All right, a little more involved. This would end up being 100 times 50 squared, which is 2500 times 100, which I think is 250,000. Still should be pretty fast, relatively fast, but fast enough. But this is definitely more involved. So now what we're gonna do is instead of just processing every edge, we're gonna say process all the edges in the one edge at a time and like recurse that way. So yeah, we could do 1, 3, the current value. And then basically we just update this value, make this a const, just update this to each iteration, just update increment j. Actually, don't even do that, just do a little confusing, but this is very confusing now, actually, I don't know. 1, 3, 1, 4, 1, 5. 3, 1, 4, 1, 5, and then we clip 1, 3, 1, and then now we have 1, 1, 4, 1, 5, right? And then now we want to clip 1, 4, 1. You know, I'm wondering if maybe this is is supposed to be used as a heap solution, heap-based solution. That could be actually what it's supposed to be. Yeah, might be easier than I realized. It's got to clip one of these things, and the question is, well, which one do you clip and why? So we clip 1, 4, 1, and then we end up with now 1, 1, 1, 5, and then we can clip the last one is 1, 1, 1, 5, and then the last thing we have is a triangle 1, 1, 1. We're done. So yeah, one of these vertices gets clipped. We got to pick a vertex to clip at the particular iteration. Okay. I don't know. Outer vertices. Pretty sure a dynamic programming solution is what I want here. Actually, you could think of this a lot like the pop balloons question that we saw in the past. Burst balloons. So you can pop 3 and you get 1, 3, 1. You pop 4, you get 1, 4, 1. And then you pop 5. Although it has a loop around, you get 1, 5, 1. Loop around back to the beginning. Excuse me. Yeah, I'm pretty sure the burst balloons question, you could do it using dynamic programming. And, wow, it's taking me a long time, huh? Yeah, the way you do the burst balloons questions, you go backwards. You would say, well, actually, the fact that these are all still connected in a circular way is a good thing to think about, good thing to consider. It makes it a little bit more complicated than the burst balloons question. Let's try this. Okay, 1 3 1 4 1 5. Let's try to do like a triple DP. So the way the burst balloons question was is you go backwards the solution. So you say each of these indices, we could say this is going to be the last thing we pop, right? So from I from 0 to n minus 1, the last thing we pop. And we select one of those, and then we say, okay, there's the right subcase and the left subcase, which can be, again, DP arrays can be used for those have some, I sub 1, J sub 1, and I sub 2, J sub 2. Recursive routines, and we want to minimize those values. And what's interesting is because 4 is the last thing that gets popped. Yeah, we pick the last one to get popped first, right? What are the values on the right side and the left side that it gets popped against? Is the question. It's not very obvious, right? I'm not really sure. Actually, I don't remember how to solve this one. Even just the regular burst balloons question, that's the basic idea, is that for each index, you can basically pick that as the last balloon to pop. Google is so creepy. It's way too much personal data. Anyway, I think in the other solution I was trying to maximize, in this solution I'm trying to minimize. Don't think it matters that much though. So if I minimize on the left side and minimize on the right side, then how can I calculate what the pop value is for this balloon? Or removal value is for this vertex? Well, it's the last one to remove, right? So we've got stuff already. Maybe all I need to do is just return as part of my function the minimum amount and the balloon value of the last one that gets popped on the left side and the right side. So if I know those two, right, then I can calculate what this one's going to be too. Maybe that's the way to do it. That's the way to go. So there's the minimum on the left side and the minimum on the right side in terms of which one gets popped last on both sides. And then multiply that by this number. Multiply that through. Now the question is, That's not necessarily the best thing to do. I don't really know what to do actually there. Good question. I don't know. I have to I can really think about this, huh? I don't remember how that one's solved. Even just the burst balloons question. That one you're trying to maximize the product. This one you're trying to minimize the product. This really shouldn't be so hard. I think. Oh wait, never mind. Hold on. No. I'm getting confused. I'm still thinking about it going in the forwards direction, that this is the first balloon you pop. Or something like that. No, because the last balloon you pop, it means that everything else is gone. All the other things are popped already. Yeah, so I think what makes this a little bit confusing is that we're actually leaving something on the right side and on the left side. Yes. The last thing we pop actually leaves something on the left side and the right side. That's why it's confusing. Otherwise we can calculate it directly. The last one. It's just whatever the value is. But here we have a few different choices for the last triangle we can have. I don't know if I can adapt the burst balloons solution to this one. It seems like you probably could, but it's actually pretty complicated if you don't have a like the remaining balloons on the left side and the right side. Maybe actually I do want the burst balloon sequence, and I just don't go all the way through it. What am I missing here? Okay, 2 hours. Yeah, I don't have a solid solution to this. I don't know. Still kind of thinking it through. Problem I'm having is that maybe the last few elements, one, I'd have to adapt the burst balloon solution a little bit. Like, it's like 2 things I'd have to do if I want to use it. Excuse me. One is that we're no longer we're wrapping around now for these calculations, which makes things more complicated. I'm not sure exactly what that would do. And the second thing that makes it more complicated is that we're not going all the way through, and we're kind of stopping part way through, where I'm wondering if there actually could be a different sequence you get if you go all the way through, and that's a different from if you don't go all the way through. If it could make enough of a difference. I suspect that it could. Doesn't seem likely. Seems very unlikely, but it seems like it's possible. Which, that would be kind of unfortunate. I'd want to prove that this works fine in that case too. Yeah, I don't know. Think about this. I guess what I could do is just, take my element in the middle, or take my element, whichever one's going to be, right? So 1, 3, 1, 4, 1, 5. And I could say for each element, there's a left side and a right side to consider. And I pick one of these elements and I say, okay, that element's going to be the last one to get last vertex to get processed, to get clipped. And then I'm going to say, okay, what am I going to clip it with? Well, there's something on the left side and there's something on the right side. And I could have, for each possibility on the left side, there is the value itself. So we'll just say L sub v and R sub v, right? Left side and right side. There's an array of values that gets pairs of values. and then the min value, but m sub v, left v, and then, I don't know, minimum LV, something like that. And the idea would be of all of those possibilities, right? The value that I'm going to select is going to be that L sub v times R sub v times, let's call it v. Depending on which selections I make, and then I have to add m sub L sub v plus m sub L R sub v. It's very confusing, these variable names. And minimize that over all the possibilities, which there are, yeah, it's quite a few possibilities there. Left side gives you, and I guess you got to take the Cartesian product of all those possibilities too. Taking the minimum of those things. Huh. Interesting. I don't know. I'm gonna go lay down for a minute. Don't know the answer. Don't know the answer. I'm thinking the burst bubbles approach is probably not the right way to go. Burst balloons, rather. This being a circular array maybe has something to do with it. Okay. Well then, maybe think about it in a slightly different way, I think. Huh. Yeah, there's some sequence that I clipped these vertices out so as to minimize the total product. It's a good question. It's pretty challenging. I got stuck on it, basically. I'm pretty sure it's some kind of DP solution, I would guess. Huh. Excuse me. Gee. Okay, well, you could say basically they're vertices that are not going to get popped at all, right? There's two vertices that don't get popped at all, never get removed, never get clipped. Yeah, that's really one of the ways. Excuse me, this is different from the burst balloons question. Two vertices that never get removed or clipped at all. I suppose I could select those two and recurse from there. Although that seems kind of bad because it's 50 choose 2, which is a quadratic number of those, and then you're going to multiply that by like a cubic algorithm. That's probably not the way to go. I don't think so. I don't think so. Ooh, excuse me. Could maybe make this a little more complicated and just have a number like cubic times a constant, where the constant is like 3 or so. And I basically just say if my counter is more than 2, I guess it would be 2. Excuse me. Then the equation I use to calculate how much is going to be added is different. Yeah, I think that's the way to go. Okay. Sure. It works. Interesting. Okay. I think they could do it that way. I think I could do it that way. So I would, so for the first two counts, I would look for values that are, well, I'm not going to add them at all to my results, but I'm still going to select those as the last vertex to process and the second to last vertex to process. So those two won't get processed at all. And then, but they will come into play. They will be meaningful for the rest of the recursion. So then I can recurse on the left and right sides of each of those. I don't know if that makes much sense, actually. I don't know if that works. So we pick one vertex and we say, okay, we'll process that one last. And then we want to recurse on the left side and the right side. And there should be one other vertex that we select that's processed last again. Processed last as well. Gee. Excuse me. That's not quite right. Not quite right. Hmm. Excuse me. Trying to even just remember the burst balloon solution, I think. Well, the last balloon to pop means the other two, the left side and the right side, have already been popped. Right. So. Which there's a default value for the burst balloons question of just 1 and 1. Interesting. Excuse me. Yeah, that makes sense. I see that, how that works. I could say if there's nothing on the left side, you just multiply by 0. If there's nothing on the right side, we'll also multiply by 0. Could do it that way. Although technically it actually wraps around. Could wrap around. If it wraps to itself, you multiply by 0. Or you could wrap around if it wraps around to something that's too close to it. Then it also returns 0. That might be a better way of doing it. Oh, you know what? I forgot something. I'll be right back. Forgot something again. Forgot something again. Yeah, I don't know. I gotta like really think about this question. Both of those questions. I don't remember how to solve the other one, and I don't realize not able to see easily how that other solution can be adapted to this one. Excuse me. I'm pretty sure it can. Both of those. I'm pretty sure the other one is not too hard, and I'm pretty sure this one can be adapted. Let me come back to it. Just give me a minute here. I'll be right back. Okay. Alrighty. What are we doing here? So, a challenging question. I'm also okay. So the burst balloons question, I'm pretty sure top time memoization would be like you would look through each value left to right, 1, 3, 1, 4, 1, 5, and you pick one of those as a possibility for the last balloon to pop. And then you would process the left side and the right side. And because it was the last balloon you popped, the burst balloons question, the calculation is just 1 times 4 times 1, because the left side is out of bounds and the right side is out of bounds, right? Then when you process those two what you're going to do is you're going to take that amount and add that to the minimum of the left side, or the maximum of the left side, excuse me, the maximum of the left side, the maximum of the right side, those values, those amounts, which then those on, when you process 1, 3, 1, pick some number, let's say 3, and then again on the right side we have a 4, and on the left side it's out of bounds again, so you have 1 times 3 times 4. So that can be calculated. Because 4, we pop that balloon last, so it's still there to be used on the right side. All the other balloons will get popped and moved out of the way. And same thing on the right side. For 1, 5, you can do 5, and the right side's a 1, and the left side's a 4. And, keep recursing. And you just memoize on the indices I and j for the left side and right side, basically the beginning and end. And then and the calculation is very straightforward. It's just whatever value you pick, multiply it by whatever's to the left of your bound and to the right of your, I'm basically I minus 1 and j plus 1. Sort of an array of I minus 1 times array of j plus 1 times, let's call it the pick, array of p or something, array of, or array of k. And, the array of I minus 1, array of j plus 1, all those get modified in the burst balloons question. If they're out of bounds, then it just becomes 1. That's it. Very straightforward. You can actually make a DP out of that. You don't really even need to use a top-down memoized recursion. Don't really need to do it that way. I'm pretty sure you could use just straightforward DP. That's the burst balloons approach. This question is very similar. It's just what's going to happen is the first thing you pick, the first pick, you're going to have a 0. You're going to have to multiply by 0. And so basically, if you're out of bounds on the left side, out of bounds on the right side, normally you would basically wrap around. So somehow for the first selection you have to have a 0, and then when you select on the left side and the right side, this time it's minimums rather than maximums. Let's say we pick 3 on the left side. On the right side we have a 4 to multiply by, and the left side's out of bounds. And the question is, because I'm wrapping around, makes things a little more complicated. I'm actually not deleting. See, that's the question, is the wraparound makes it more complicated for sure. Because I don't know which one's going to be there or not be there. If 3 is going to be actually going to be processed, and I need to wrap around, let's say it's to 5, so it's going to be 5 times 3 times 4. Or if it's the other way around, if 5 gets processed first, and so it's going to be 5 times 3 times 4, and then the 3s and the 4s that just don't contribute anything. Yeah, it makes it quite a bit more complicated. Actually, it comes to a totally different solution. Totally different solution with different ideas for how to do this. I don't know. I don't know. Well, actually, even if I process the 3 or the 5, because it wraps around, it doesn't matter which one I process, right? Because it's still, both of them are going to reach the 4 on the left or the right, and then they're going to reach each other when they wrap around. So that's not that big of a deal, I suppose. Interesting. Interesting. Huh. I don't really know. Well, okay, the wraparound does matter though, because I need to know what the state is of the left side and the right side in order to process those. Yeah. Yeah, it makes a big, that actually matters quite a bit, I think. By the way, I think all of the possible triangulations, I think there are quite a few different possibilities. It's not obvious exactly how to go through all the possible triangulations. I'm thinking maybe there's a different approach that's not based off the burst balloons idea. Excuse me, I don't know. if I had something like 1, 1, 1, 1, 3, 4, and 5. I wonder what kind of triangulation would be giving the minimum here. So 3 of these need to be clipped. This one maybe. Oh, no. Wrong. I don't know. Try to do some of these by hand here. See if I get any ideas. I mean, every edge has to be part of some triangle, that's for sure. Right. Let me go back to the first recursion that I had. That seemed pretty good. The idea of like just sort of drawing one line at a time. Definitely you get subcases doing that. And I don't know, man. Not obvious. Maybe I should Still trying to figure out the answer. I should put this over here. Tough one. It's a tough one. Definitely a tough one. I wonder if a greedy algorithm works here. I don't think so. Just curious. Yes, tough question for sure. The thing that's kind of got me is that I'm trying to optimize. I'm trying to get something that's like a recursion that can be optimized using dynamic programming. It's not obvious how to do that. Yeah, I was thinking like clipping points out might be the way to go, one at a time. That doesn't seem very good though. So when you have a triangle, you really only have one choice, right? And you just return that amount. You have a square, two choices to pick from. You could have basically 1, 3 present. You have vertex 1 to vertex 3. Or you could have on the other side, you can have vertex 2, vertex 4. So we end up with 8 times 4 on one side and 3 times 8 on the other side. So 3 times 8 is better. Well, it's not obvious which one's better, generally speaking, but I guess you could calculate those two and choose between one or the other. When you have 5, it gets a little more complicated. pentagon. I think you have quite a few more choices for the pentagon. Yeah, you could do the one of 4 sides first. Excuse me, one of 5 points first. Okay. Yeah, 1, 2, 3, 4, 5. That's 5 of them. Yeah. And again, I realize you can't really see what I'm doing here. Can't really see what I'm doing here. There should be 10 total. I think that's right. Yeah, it's 10 total. Okay. Left, top, right, and bottom left and bottom right. And then you've got, that leaves you with the foregone. And that can be split into two different options to triangulate that. Yeah. Excuse me, so there's 10 possibilities. So 5 gives me 10 possibilities. 4 gives me 2 possibilities. How many possibilities do we have for a 6-gon? 6-gon, you can clip one of 6 different vertices. And then you left with the 5-gon, which has 10 possibilities each. Gives you 60 total. And the next one is 7. 7 times 60, 420. And so it's kind of like a factorial already. You have 7 times 6 times 5 times 2. It's 1. You have one way of doing 3-gon, 2 ways of doing a 4-gon. Oh no. Oh yeah. And then you have 10 ways of doing a 2 ways for a 4-gon, and then right. It's a little weird how it works, but it's kind of like a factorial. It's almost a factorial. It's just missing a 4 and a 3 in there. It's like a factorial divided by 12. 7 factorial over 12. And factorial over 12. Just skips 3 and 4. But everything following all the n-gons after that, it's basically a factorial number of ways you can. That would explain why my brute force solutions were not working. There's a lot of possibilities there. It's factorial. Yeah, for even the foregone, yeah, it's 4 factorial over 12, which is 2. And the 3-gon, 3 factorial over 12. 3-gon is 1. Yeah. So we could say like g of n, n factorial over 12 for n greater than or equal to 4, and 1 n is less than or equal to 3. Really is not even defined when n for less than 3 doesn't even exist. But yeah, that's how many possibilities, how many possible ways this could be triangulated. Interesting. But how do I optimize, right? How can I optimize this? Well, good question. Can I do this in quadratic time and I just don't realize it? Maybe, I don't know. That's a good question. What's really awkward about this is I don't think there's any of these, none of these pictures like overlap with each other, if that makes sense. Like none of them have there's no like aside from these all being foregons, they all are different from each other. Like if each vertex has a unique value, then every n-gon after I clip one triangle is basically different. Well, okay, they're not different. I would say you can reuse only some of the solutions. So for the first vertex, you have you have n for each step. You have n choices, n possibilities, and then each of those now have n-1 possibilities to consider, and then it just keeps going. Like you just end up that's a pain in the neck, huh? Almost looks like it could be a really straightforward DP from taking that approach, but it's actually a little more complicated than that. Yeah, because whatever choice you pick, each of these lines, there's only, there's n possible choices. And then each one you get some triangle plus f of n minus 1. But it's not just f of n minus 1, it's 4 fewer points, but those points are potentially different from each other in each case. Excuse me. I suspect a greedy algorithm is what you need here. It seems like a DP algorithm, just not really that good. It doesn't really fit. Suppose you probably the line that you take is probably just going to be the two smallest values each time. Points the two smallest values. Or maybe it's just the triangle that gives you the smallest clip. When you clip it off, smallest amount. That's it. Just really straightforward. I mean, does that make sense? If that's correct, I definitely don't have a proof for that. I don't know. Oh, LeetCode questions can be so hard sometimes, man. Really, it's just, I don't know. How many hours have I been on this? Almost 3 hours. It's frustrating. It's very similar to the burst balloons question, I have to say. It's like tantalizingly close. Difficult, very close. Tantalizing, is that the right word? Tantalizing. Yeah, it's about right. That's about right. Can I go backwards in this one too? I don't know that I can. Pretty sure I can come up with an O and the fifth solution. Basically take O(n) squared time to choose two elements, two vertices that are going to be present in the last triangle. And then from there, you just select back to front which vertices are going to be the last one to get popped. All the possibilities you could select are left over. And since everything's gone, the only last two vertices would be the ones to process. I guess you'd have to recurse on every like intermediary section, subsection. Yeah. Or not recurse, like run a function on all the sections, subsections. Yeah, basically, you would wrap around when processing an element. I would wrap around. But I would wrap around all the way to that's a good question. No, it's not obvious what to do here. Yeah, the wraparound's very confusing. Now the burst balloons question is a little bit different because they don't have the wraparound. The wraparound really makes things a lot different from the burst balloons question, I think. I think because of that, maybe you can just do a greedy algorithm. I'm starting to think maybe that's what it's supposed to be. So you basically have to include all of these elements at some point. It's a tough question, man. I don't know. Don't see it. I don't see it. I'm trying to think of like some solutions that I could do by hand, some ideas, but nothing's coming to mind. Nothing too useful is coming to mind here. Oh. Gotta think about this. Gee. Yeah, I really need to think about it. You really need to think about this. I don't know. Wonder if the greedy algorithm is just find the smallest element and then just process the node to the left or to the right that's smallest, or largest rather, largest. So we always have the smallest elements available. Processed on the larger elements. Wonder. It might work, I don't know. It's got to be some kind of greedy algorithm. It's a little bit too complicated for the dynamic programming and the recursion solutions. Although that seems like very fast if it's just a greedy approach. Seems like it probably should be a little more than just that, but that might be it. Excuse me. Maybe I should try to use DP and do like a wraparound array where if I is greater than j, then it's considered to be a wraparound array rather than rather than two separate things that need to be processed. Maybe I could do it that way. That might be better. Wondering. Okay, maybe I've figured it out. I'm a little bit tired though. Maybe I want to just make this a part 1 and do something else. Okay, I think the way to do it is to make 2 adjustments, and then yeah, basically it's like the same solution as the burst balloon solution. The 2 adjustments are going to be 1, make the arrays wrap around and handle that, so that way if I is greater than j, then it's a wraparound, otherwise it's not. And then also make the recursion operate differently depending on a count variable, which lets me know. It's like a third extra parameter. It's also memoized that just lets me know if I've already selected the 2 last values that'll get processed. And if I haven't, then all I'm going to do is just select 1 element and then recurse on a wraparound array. The first one and the second one is going to split that wraparound into 2 arrays and recurse on those 2. In both cases, it's going to, depending on the count value, it's going to just return 0 for the amount when selecting those 2 variables, those 2 indices. And then when count is larger than, or is greater than or equal to 3, or when it's 3 really, just not greater than or equal to 3, then it all functions normally again with some wraparound variables in there, wraparound arrays, and yeah, and then I just end up with a cubic time algorithm with a constant multiplication factor for the count variable. So yeah, I can just add a count variable and a wraparound. I think that works fine. And do top-down recursive memoization. I think technically, at least in theory, I can do. I could also do this using DP, but I think it's a lot more complicated with using DP, or a little more complicated using DP. It's not obvious how to convert that from what I just described to a DP. I'm not too sure about that, but yeah, with the wraparound variables, it's a lot easier to think about. I believe, a lot easier to process. Yeah, I think I'm gonna take a break here. I'm not gonna program all that now. Just don't want to. And it could be wrong, and then I'll be disappointed. I kind of want to eat some food. Yeah, because I've been at this for a few hours now. It's kind of expecting to go like, quickly through the questions, do 15 minutes here, and then 15 minutes there. But this took me a really long time. Excuse me, I don't know. 3 hours. 3 hours is a good amount of time. It's not a lot of time, but it's a significant. It's not nothing. Also, it's only 8:30. It feels like it's so late. I'm gonna go. So thank you for watching. I'll make this a part 1, and I'll probably cut the video too before I upload it. Actually, no, I think it automatically uploads. I don't think I even need to cut anything. So whatever, that's fine. There's like a good 20 minutes where I just have a black screen, or so however many minutes. All right, so thank you for watching. Talk to you soon. Like the video, don't forget to like it. Yeah, this is a tough question. It's a challenging one. I don't know what to say. I think I had to really think about it. So we'll see. We'll see if the idea that I have is correct, and then maybe I can come back to it later too and do a Reddit DP solution. But yeah, I'll update this to a part 1. Make a part 2 later. Yeah. All right. Take care. Talk to you soon.